One of the common tasks that we'll have in machine learning is optimization, specifically continuous optimization that deals with algebraic functions. So let's just look at something from a Calculus 1 course we would see. We would want to find, say, the extrema, or the minimum and maximum points of f of x equals x cubed minus 3x squared plus x plus 7. Well, one of the things we've been taught to do is to take the derivative and set this derivative equal to 0. So its derivative would be 3x squared minus 6x plus 1. And then we would set this equal to 0 and solve for x. And that would at least tell us where the critical points are. And the critical points might be minima, they might be maxima, they actually might be neither. And so the first objective that we would have is to set this equal to 0. Now this particular process right here is not that sophisticated because, well, we could solve a quadratic equation without too much problem. But imagine that this is a quartic, x to the fourth, and the derivative becomes a cubic. And, well, setting that cubic equal to 0, it's still possible to find the values of x, but it gets harder to do. And so this is just one example of where we already have to decide what kind of function we have, how do we find its roots, is it even possible to find its roots? Specifically when we're dealing with, let's say exponentials and trigonometrics, and setting it equal to 0 could get very complicated very fast. So we don't often take this approach even when it is possible, right? So instead, what we do is we approach this numerically, meaning that rather than finding the critical points algebraically, we'll do this via iterative process. So we pick some point, and I guess I should have made this into a vector. And then we need to calculate the gradient at this point. What we do know is the objective is typically going to be to minimize a function in machine learning. Usually it's going to be an error function, and we want to minimize the error in what we're doing with that machine learning algorithm. We want to move in the direction opposite to the gradient. And remember, gradient moves in the direction of maximal rate of change. Therefore, to move towards a minimum, move in the direction opposite the gradient. That is, if the gradient of f is known to move in the maximal rate of change direction, then move in negative gradient to descend quickly towards a minimum. Now, this is really in higher dimensions. This doesn't, in a two-dimensional graph like this, where you only have one input variable, the gradient is really just the derivative at that point, and the derivative doesn't point in the maximal rate of change. It always points in the direction of increasing x. So it's a little bit different here, but let's go ahead and illustrate this. So let's say that I picked, in this case, my x naught vector is just a point, and that's just a value. So that value, let's say I chose to be 1. So what I would do is I would calculate the derivative at that point. And the derivative would point like this, right? And so I would get a negative slope at that point. Specifically, if I plugged in 1 into my derivative, I get 3 minus 6 is negative 3 plus 1 is negative 2. So f prime at x naught would be negative 2. And that tells me that if I increase x by 1 unit, I would, in theory, drop or decrease the value of f by 2 units. All right, so that tells me that if I move in that direction, in increasing x, that I'm moving further towards a minimum, right? Now, if I went 1 unit in that direction, then I might actually end up overshooting it. In fact, if I increased x by 1, then I would actually end up at x equals 2, right? Suggesting that if I move in the direction of increasing x, that I'm going to decrease my output, but it's possible to overshoot, right? Because now you can see that our value of f has actually decreased, but it has decreased by less than it could have, right? In other words, the minimum is right here, but we have overshot that point. But nonetheless, the derivative tells me which direction to move in this case, to move towards the minimum. But the question is how much should we do that by, right? But I just wanted to illustrate the idea here. Now, one natural problem is choosing the starting point, right? If we have no idea, if we're doing this via a computer algorithm, then we may not have any idea where that starting point is. Later on, we'll consider a type of function called a convex function that makes that a little bit easier. Now, let's also consider what this might look like in R3, where now we actually do get gradients that are more than just a value. So I'm going to go ahead and jump over to this utility here and illustrate something about three-dimensional functions. Now, at every value of z, okay, so z is this blue axis moving up, and you can see that we have this paraboloid. It looks like a three-dimensional parabola. And as I move this value up, what that's going to do is that's going to control the height of z. That's going to be this black plane that you see here. And what that black plane is going to do is, because it's horizontal to the xy plane, this gray area consisting of the x and the y axes, as you can see here, it is parallel to that. So it's going to slice through horizontally through our paraboloid. Now, if we look at this from above, we can actually see where that slice has formed. And more specifically, we can see the contour of that slice. So the contour seems to indicate that the way it slices it, if you were to take the two halves, the bottom half here and the upper half here, and separate them at this slice, what you would see is that they connect with a circular shape right here, which is actually what I have graphed over here. That right there is the contour ring, basically the two-dimensional contour of the top half and the bottom half of this paraboloid at that slice. Now, if I move that slice downwards, what we should see is that that circle is going to get smaller. So watch what happens as I move downwards. You can see that now that circle is much smaller. That contour is a smaller circular ring for z equals 1.8. I have it labeled here as a, but that's fine. And then, if you get down to right there, well, that's just touching it at one point. You can actually see there that's actually intersecting or touching the paraboloid at its minimum, right? So that point actually indicates minimum. And as a grows, that circular contour gets bigger. So now imagine that what we did is we plotted a bunch of these contours. So we know that, right there is our minimum. And as we change this value of a, it just makes that contour bigger and bigger and bigger. Okay, I'm doing a very bad job here of drawing this. Okay, so just to roughly illustrate this, right, we get this next contour ring right here, and so on. Okay, and the reason I'm drawing this is because we're going to have some gradient function for this. We're going to have the gradient of f of the vector x. Now the vector x in this case consists of an x and a y, but we're using the vector notation to indicate this could be in 3 or 4 dimensions, and we could have xyz or wxyz or whatever. Now in the context of gradients, if you are at a specific point, let's say -1, -1, and you calculate the gradient at that point, it is actually going to point in the direction of maximal rate of change. So let's imagine, here is -1, -1. It's right there. That's the point on the paraboloid right there. And it is now going to point in the direction of maximal rate of change. So as you can see, it's going to point upwards like that, right? Well, in terms of the direction that it points, in terms of x and y, it's going to point kind of outwards, right? So one thing that we know in multivariate calculus is that the gradient vector is actually perpendicular to that contour. Okay, it doesn't really make a big difference here, but I'm throwing that out there. It's going to be perpendicular to that contour. And that's why it moves in the maximum rate of change. It's going to move you to the next contour as quickly as possible. So that's going to be the gradient of f. And then the negative of the gradient of f is going to point in the opposite direction. And as you can see from the illustration, the negative gradient is going to point back at towards the minimum, right? It's going to point back towards the minimum. So in the three-dimensional context, we would actually want to descend this way. So we'd actually want to move inwards towards that origin. And that would, ideally get us closer to the lower contours so that we get towards the minimum and figure out what that minimum point is. Okay, this process of doing this, of moving in the direction opposite the gradient, is called gradient descent. For a good reason, right? We're descending by descending the curve by moving in the direction opposite the gradient. Okay, let's formalize this a little bit. Our goal is to find the input vector x that minimizes f of x. That is, find the minimum of f of x, this is what we're minimizing, right? We're finding the value of x that minimizes f of x. This is the notation that we typically use. We're in RA, meaning that our x vector is gonna have a components, x1 all the way through xa. And what we're gonna get is an output here as a single number, right? That means that you can plug in a bunch of inputs, but you're just gonna get one output. At each point, we obtain a gradient, a set of slopes. We want to get the minimum, so we make a move in the direction opposite the gradient. But the question is how much movement in that direction, right? Up here, we saw that if you move that full 1 unit, this is -2/1 per 1 unit, then you would actually overshoot that minimum. Well, the same thing can kind of happen here, right? The negative gradient of f of x is per 1 unit length in each direction component of the vector x. So if we, for instance, found that the gradient of f is say, I'll just make these constant, 2, 3, then this is f sub x, meaning this is 2 units of increase of f per 1 unit increase in x, and this is f sub y, this is 3 units increase in f per 1 unit increase in y. So that's what I mean by this. That's for each directional component of the vector x. If we want to move, say, half a unit instead of the full 1 unit, then we could just scale this by 1/2. So if we took 1/2 of this gradient, then we would get 1 per half unit, 1 per half unit, and here we would get, in the second component, we get 1.5 for a half unit. So what that would do is it would make our step smaller, and we would be less likely potentially to overshoot that minimum. Now, of course, we're moving in the opposite direction, but I wanted to illustrate just what I'm saying here. By cutting it in half, that would be per half unit change. In general, we want h multiples in that direction. H is typically what we use to indicate how much change there is in an input. Then we would move negative h multiples of the gradient, and we call h the step size. Furthermore, if we choose a point to start this process, x0, then to get the next point, we move to x, we'll call that x1, and how do we get x1? Well, we take our current x and we move h multiples in the direction of the gradient. So we're going to look at an example here momentarily of how this works, but visually what I want you to see is that, if you started here and that was your x0, and then you moved here and that was your x1, well, then you would continue to move until when? Well, until you got to a minimum, and you would know that when that x stopped changing. So you would kind of keep repeating this. Then you'd get x2 by going from x1, h multiples in the direction of the opposite gradient. And you'd kind of repeat this, right, indefinitely or until your next point and your previous point are approximately the same, meaning that the point converges and ceases to change, indicating we have located a minimum. All right, let's take a look at an example now. That paraboloid that we were looking at was the function f of xy equals x squared plus y squared plus 1. That's what we were looking at in this three-dimensional graph here. The gradient of that function would be 2x and 2y. And let's suppose that h equals 0.5 is our step size, and we start at the point 3, 5. Okay, so that's our initial point. So x naught is the point 3, 5. To get x1, what we would do is we would take our current point 3, 5, and we would move half of the gradient vector at that point. Okay, what's the gradient vector at that point? Well, at 3, 5, the gradient vector at the point 3, 5 would be 2 times 3, which is 6, and 2 times 5, which is 10. And we are moving in the opposite direction of that, and also only half of the unit. So half of 6 is 3, and you can see that that would give us 3 minus 3 is 0, and then 5 minus half of 10 is also 0. So notice that in that case, we actually coincidentally moved right onto the minimum. And if you continue to repeat this, x2 is equal to our x1, which is 0, 0, minus 1/2 of the gradient at the point 0, 0. Well, if we are at a minimum, guess what the gradient is going to be? Well, the gradient is going to be 2 times 0, which is 0, and 2 times 0, which is 0. Therefore, our gradient is the 0 vector, and x2 ends up being the exact same point, so we must be at a minimum. Or at least that's what we think, right? Now, I mentioned a moment ago that there's going to be a problem with this, and the problem is that if we picked a step size that typically isn't going to be right, I just happened to establish this problem this way so it would work out like this, but let's say we picked h is equal to 1. Well, x0 would still be the vector 3, 5, and x1 would now be the vector 3, 5 minus 1 full multiple of 6, 10, and that would give us -3 and -5. Now, if you've noticed what we've done here, we've gone from 3, 5, we were wherever this point is on this contour, 3, 5 would be somewhere, off this grid, but 3, 5, and now we just moved to the point -3, -5, so we're way over here now in the xy plane, right? So what we've done is we've overshot from a point somewhere over here to a point that is now over here. And you can see that we went straight across to, and then remember our f value is somewhere way up here because this paraboloid keeps increasing. So as we move further away from the origin, we're way up high, but this paraboloid, of course, is only drawn to give us the visual. So we've just gone from the point 3, 5, 3, 5, to the point -3, -5. Right there, right? We've just overshot that minimum. Here is the minimum we want to get to. And if we repeat this again, x2 is now equal to -3, -5, minus 1 multiple of the gradient of f at the point -3, -5. Well, what would I get if I did that? Well, if I plugged in -3, -5, it's going to be 2 times -3 is -6. 2 times negative 5, which is negative 10. And so now I am going to add, because it's negative 1 multiple of that, I'm going to add 610 to negative 3, negative 5, and guess where that's going to put me? Well, it's going to put me back at the point 3, 5. And so basically we're back at this point up over here, and as you can see with this step size, our next move will just bounce us back over here, and we're just going to keep on toggling between these 2 points, and we're just going to keep on jumping. Sometimes it ends up being a zigzag. In this case, in this example, we're just bouncing back and forth between these 2 points. And we're not going to get any clear convergence. In fact, we're just going to get an infinite loop between these 2 points. Now, this is just one example of this step size going wrong. There are, of course, situations where you just kind of end up bouncing around the minimum but never getting clear convergence. Now, it's never going to be like a perfect convergence, except, like you noticed up here, this was a perfect convergence in one step. That's very rare. You usually are going to say, well, we believe it's converged once the change in the output is, or the change in that point is like a preset amount of smallness. So in other words, you might say that, okay, once our x and y change by less than 0.1, we're going to say that's good enough, and we've approximated a minimum. So how do we approach this in the case where the step size causes these problems? Well, if f of x gets larger after a step in the direction of the negative gradient, the step was too big. So undo the step and make the step size smaller. As a bonus, if f of x gets smaller after a step, this means the step size could have been larger. So undo the step and make the step size, I should say larger. So it's kind of like we don't move. Let's not move until we know what effect that's going to have. And we can check what effect that's going to have by looking at the next point and seeing if the value of f at that point has gotten bigger or smaller. Now, these are just heuristics. These are kind of like mental shortcuts. But the end goal, the end result here is we should probably not use h, as this seems to imply a constant step size. And let's denote the kth step as having a step size of h sub k, implying at each point the step size is somehow recalculated. And the question is, how do we do this? Well, we're going to need to account for the fact that our step size needs to be more sensitive near the minimum. And so in general, what we'd say is that to get the next input that we'll move to, take the current input vector, subtract away h sub k. So this is our kth step size, which is going to be recalculated, multiplied by our gradient at x sub k. And that is where we'll leave this. The question that we have now is, how do we calculate that? How do we get that so as to make the convergence optimal?